This is truly an extraordinary moment in space exploration, and it's all about 3 Atlas, an interstellar object that's been defying expectations. Let me walk you through the latest findings that are shifting the narrative around this object. We're not just talking about vague speculations anymore. We're diving straight into the data, analyzing what's really going on, and how it challenges everything we thought we knew about interstellar comets. Stick with me through this breakdown, because in the final minutes, I'll connect the dots between these findings in a way that's crucial for understanding the bigger picture. First up, let's talk about water. Yep, water. 3 Atlas has just delivered an unexpected chemical signature even farther from the Sun than scientists anticipated. A team using NASA's Swift Observatory picked up a hydroxyl signature, which is a key marker of water breaking apart under sunlight. And what's even more surprising is that Swift detected this signal when 3 Atlas was about 3 times Earth's distance from the Sun, much farther out than comets usually start releasing water. Now, that's a huge deal because classic comet models predict that at such a distance, water sublimation should be minimal, but the data says otherwise. 3 Atlas is losing about 40 kilograms of water per second, sustained, active outgassing from an object that should be relatively dormant at this point in its journey. This raises an important question. Is the gas only coming from the nucleus itself, or are tiny icy fragments around it acting as mini evaporators, each releasing material at their own rate? The second possibility suggests something more dynamic, like a moving cloud of ice, each chunk behaving differently based on its location and exposure to sunlight. And that could explain the object's changing appearance from observation to observation. This one number, 40 kilograms per second, is crucial, and I'll show you in a bit why it might matter even more than all the dramatic commentary about this comet combined. Now, let's move on to the second major update. This comes from a different instrument, NASA's SPHEREx, which observed 3 Atlas during its close approach in December. And guess what? It detected organic molecules in the outflow of the comet, including methanol, cyanide compounds, and methane, alongside water and carbon dioxide. This isn't just one blurry image, it's a complete compositional map showing multiple molecular species in parallel. Dust, water, organics, and CO2 all tell different stories, all of which add new layers to our understanding of what's going on. The question is no longer just whether the object is active, but what exactly is active, where, and in what proportions. For scientists tracking the volatile evolution of these objects, this is precisely the kind of detailed data they need. And yet, there's something important to clarify. Just because organic molecules have been detected doesn't automatically mean biology is involved. NASA itself pointed out that organic compounds are often the result of non-biological chemistry. Organic simply means carbon-bearing molecules, not necessarily life. So, anyone who tells you that this detection confirms life is overreaching the data. But what's critical here is the pattern. This object is showing robust outgassing with organic compounds, water, and other chemicals in a way that seems unusually diverse for a single comet. That combination, occurring during a brightness surge period, is why researchers are so fixated on it. It's not a smoking gun, but it is a converging signal, and converging signals are exactly where groundbreaking astronomical discoveries tend to begin. So, what does this all mean? Well, it changes the conversation from "is it active" to "what exactly is going on and why?" One of the key takeaways here is that our models of icy bodies and where they form in other star systems are being put to the test. 3 Atlas isn't just adding one more sample to the mix. It's pushing the boundaries of what we thought we knew. And while this doesn't confirm life, it does strongly suggest that complex organic chemistry, including prebiotic molecules, could be more common in interstellar space than we thought. So, the big question remains: are life-friendly ingredients rare in the universe, or are they actually widespread, just waiting for the right conditions to develop? This data swings the needle toward ingredients being more common, but we're still far from saying anything definitive about life itself. Now, if you appreciate this breakdown of the facts, hit that like button and subscribe. We're diving into some real science here, no sensationalism, just cold, hard data. It helps a ton and allows me to bring you these updates without the noise. Let's continue with the analysis, because this is where it gets even more interesting. One of the key advantages of NASA's Swift Observatory is its ability to observe in the ultraviolet spectrum, something that's difficult to do from the ground. When Swift picked up the hydroxyl signature, it wasn't just one lucky frame. It was a series of stacked exposures, carefully calibrated to pull out the faint signals that can easily be misinterpreted in less precise data. And that's critical because faint signals are notoriously difficult to handle. If you hear someone say that maybe it was just noise, the honest truth is that faint comet signals are always a risk of being overinterpreted. But that's why we stack the data, cross-check it, and use independent instruments to build a clearer picture. And with SphereX providing broad infrared compositional capabilities, confidence in these findings is growing. Here's where things start to matter for future space missions. If the activity continues at this sustained rate, we can no longer treat 3 Atlas like a dormant rock. It challenges our basic assumptions about how comets behave, and that has serious implications for mission planning. For example, spacecraft studying comets need to plan for stronger coma structures, dust hazard envelopes, and photochemical activity than previously expected. All this affects risk assessments for future missions that might visit these objects. If you follow this channel, you know that changes in mission risk lead to changes in scientific priorities, funding, and public interest. High-quality data forces institutions to prioritize what's important, and that's exactly what we're seeing here. But here's something that might fly under the radar. The results from SphereX were shared as a work in progress, not the final peer-reviewed endpoint. This doesn't mean the data is wrong. It just means we have to scale our confidence to the publication stage. Think of it as a sneak preview of the science to come. Peer review is a crucial part of the scientific process. It helps refine the picture and identify any weaknesses in the current model. Whether the current hypothesis stands or is broken down by new findings, either way, we all benefit from a sharper, clearer understanding. So, as 3 Atlas continues its journey outward, the next phase of its observation will be key. The object has already brightened significantly during its close approach, and as more surface material is exposed, the chemistry is shifting. But here's the catch. This phase of activity may be one of the least visible to the public, as fewer dramatic images might circulate. However, the science will intensify behind the scenes. This is when patient, long-term analysis becomes the most valuable approach. If you're still with me, that's because you understand the value of deep scientific inquiry over flashy, viral content. Drop a like if you agree, and stay tuned for the next update, which will include new spectra and more precise data. To sum up this part of the story, we now have more detailed evidence that 3 Atlas is not just another interstellar object. It's a benchmark in our understanding of interstellar comets. With UV and infrared data pointing to chemical diversity and sustained activity at surprising distances, 3 Atlas is pushing the boundaries of what we thought we knew about these objects. It's not a solved puzzle yet, but it's certainly no longer an empty mystery box. Now, it's up to us to keep testing these findings, refining our models, and learning what this interstellar visitor is really telling us. If you want to keep up with the latest updates, make sure to subscribe and turn on notifications. I'll be back soon with the next data-driven update. Stay sharp, stay curious, and I'll see you in the next one. Let's dive straight back in. There's more to uncover here. So, we've talked about the big water signature and the organic molecules, but the plot thickens. The latest data from the two different observatories, NASA's SWIFT and SPHEREX, has changed the way we think about 3 Atlas. It's not just a passing object, it's becoming an incredibly valuable test case for future studies of interstellar bodies. And as new data pours in, we're starting to see that some of our old models might need a complete overhaul. One of the most intriguing updates centers on the amount of water being released from 3 Atlas. When SWIFT picked up that ultraviolet hydroxyl signature, it suggested that water is being broken apart into hydrogen and oxygen at a steady, significant rate, about 40 kilograms of water lost every second. Now, that's huge, especially when you realize that this object is still far from the Sunday. This rate of loss is far higher than what we'd expect for a comet at such a distance. The fact that this comet is maintaining such a high water loss rate at this distance really challenges the standard models for how comets behave. If the water is coming from icy grains around the object, then we may be witnessing a more complex outgassing system where not just the nucleus is releasing material, but a surrounding cloud of tiny icy particles is also evaporating. This adds another layer of complexity to the puzzle, showing us that 3 Atlas is not just a typical comet, it's a comet behaving in unexpected ways that may require us to rethink how we view these objects as a whole. This is where things get even more fascinating. The second update from NASA's SPHEREX observations revealed a much richer chemical profile than we anticipated. Along with water, 3 Atlas is releasing methanol, cyanide compounds, methane, and carbon dioxide. These organic molecules in particular have significant implications for our understanding of interstellar chemistry. The detection is not a single blurry snapshot, but rather a multi-channel spectral mapping of the object. These individual molecular components, dust, water, organics, and CO2, were all detected in separate channels, giving us a clear breakdown of what's happening at different levels of the object's outgassing. This level of precision is critical because it means scientists can now piece together how these different substances interact and what that means for the formation of these objects and, potentially, for the origins of life itself. But here's the key to understanding why this matters. While organic molecules in space are exciting, they don't automatically imply life. NASA has explicitly cautioned that organic molecules are simply carbon-based compounds, and they can be formed through non-biological processes. So when we talk about organic chemistry in this context, we're talking about the building blocks for life, but not proof that life itself exists. This is important because some headlines might oversell this data as evidence of alien life, and that's simply not what the data is saying. The real story here is the unexpected pattern emerging from this object. We're seeing a wide variety of chemicals coming from an object that's far from home, and it's happening in a way that suggests that interstellar bodies like this one could be much more chemically complex than we thought. And that's a huge deal. What's even more important here is how these findings contribute to a larger question that's been lingering in the background. Are life-friendly ingredients rare, or are they common in the universe, just waiting for the right conditions to develop into life? The data here strongly suggests that these organic molecules are more widespread in the galaxy than we once thought. While we still can't claim that life is out there, we are getting closer to understanding how the basic ingredients for life could be distributed across the cosmos. And that changes everything. The fact that these organic molecules and water-related activity are being detected from an interstellar object pushes the idea of life-friendly chemistry from something that's extremely rare to something that could be relatively common across the galaxy. But let's not get ahead of ourselves. While the science is exciting, we also need to be cautious. If we get too excited about what these molecules might mean, we risk falling into the trap of sensationalizing the data. There's still a lot of uncertainty surrounding what's really going on with 3 Atlas. Even though these updates push the needle toward the idea that the building blocks of life might be widespread, we still don't have direct evidence of life itself. The difference between prebiotic chemistry and biological life is huge, and we're still a long way from being able to make definitive claims. So when you see those big headlines saying, "Aliens confirmed," or "Life detected in space," just remember those claims go way beyond the data. What we have here is a much more measured, but no less fascinating picture of what's going on. Now, let's zoom in on the methodology behind these findings, because this is where the credibility really lies. NASA's Swift Observatory has a major advantage in that it's positioned above Earth's atmosphere, allowing it to capture ultraviolet light that's often blocked at ground level. This is a critical tool for spotting subtle chemical signatures that might otherwise be missed. And the key here is that these findings weren't based on a single lucky observation. They were the result of stacking multiple exposures and carefully extracting the faint signals from the noise. The fact that the team was able to pull out this faint hydroxyl signature is a testament to the reliability of the data, and that's why this matters. It's not just a random fluke, it's the result of careful, methodical science. In contrast, SphereX provides broad infrared capabilities, which gives us an entirely different but complementary kind of confidence. Swift and SphereX are working together to give us a fuller picture of what 3 Atlas is made of. The combination of UV and infrared data helps build a more robust case for the activity we're observing. Even though there's still some uncertainty around the exact abundance of these compounds, the fact that 2 independent methods are pointing to similar conclusions makes this data all the more reliable. But here's the operational takeaway. The amount of water being lost from 3 Atlas could change the way we plan future space missions. This new data is already pushing mission planners to think beyond the traditional assumption that comets are dormant objects. With sustained outgassing at such a large distance, we may need to adjust our models for coma structures, dust hazard envelopes, and how we assess the risk of spacecraft encountering these objects. This is not just about science. This is about the very real, practical implications for the future of space exploration. The changes in mission risk will force a re-evaluation of priorities, funding, and how we approach future missions targeting similar objects. And don't forget, this is just the beginning. One of the more subtle but important updates here is that the data from SphereX was released as a work in progress. This doesn't make it less valuable, it just means we need to be cautious in our confidence until the results are peer-reviewed and finalized. Think of it like a strong draft that's still being polished. Peer review will help refine the picture, and even if the current model breaks down, that's a win too. It'll help us understand what we misunderstood, which is exactly what we want from science, a process of refining our understanding, not settling for easy answers. So, the story of 3 Atlas is far from over. The object may be moving away from us, and it may not be as visible to the public in the coming months, but the real science is just getting started. The next phase of observation is critical, and while the dramatic images may fade, the analytical work will only intensify. For those of us following along, that's when the real breakthroughs will happen. Keep an eye on the data, because this is the moment where patient, disciplined analysis will begin to pay off in big ways. And if you're still with me, you're the kind of person who values data over noise. Drop a like if this breakdown made sense, and make sure you're subscribed so you can catch the next update as soon as the new data drops. There's still so much more to uncover, and we're just getting started. Stay tuned. Now, let's talk about where we stand today with 3 Atlas and what this could mean for the future of space science. So far, we've discussed how the new water signature and organic molecules are pushing us to rethink everything we know about interstellar comets. But there's more to the story than just chemistry. These findings are raising some critical questions that could reshape how we study these objects moving forward. One of the key questions that's been coming up is whether 3 Atlas is just a normal comet that's behaving unusually, or if it's an entirely new class of interstellar object that could challenge all our existing models. Right now, it seems like this comet is walking a fine line between the two, and that's why it's so exciting. For example, we're used to thinking that comets become active only when they're closer to the Sun, but 3 Atlas is showing a completely different pattern. The fact that it's releasing water and other chemicals at such a large distance, about 3 times farther from the Sun than Earth, wasn't something we anticipated. This activity is happening far earlier in its journey than we thought it would, and that raises the possibility that comets like 3 Atlas might behave very differently from what we've seen in the solar system. This data is putting pressure on the old models and forcing us to ask bigger questions about what's happening in other star systems. But here's where it gets even more interesting. As more data comes in, we might be looking at a scenario where 3 Atlas isn't just behaving unexpectedly, it's actually revealing a new type of chemical environment that's less exceptional than we assumed. We've already seen evidence of comets with dry or carbon monoxide-rich behavior, and now we have 3 Atlas showing up with water-linked activity and organics. This is extending the diversity map for interstellar bodies and forcing us to rethink how icy bodies form in other star systems. If this pattern holds, it could mean that the basic ingredients for life, or at least the precursors, might be more common throughout the galaxy than we ever imagined. We could be looking at a broader picture of chemistry that's more varied than we thought. But let's be clear, even with all this new data, we're still a long way from proving anything about life. Yes, we're seeing water, organic molecules, and complex chemistry, but we have no direct evidence that life has ever existed on 3 Atlas or anywhere else in the interstellar medium. The current data is telling us that the ingredients necessary for life may be more common than we once thought, but it's not saying that life itself is out there. The key takeaway here is that while the story of 3 Atlas is full of intrigue, it's not yet a confirmation of anything beyond basic chemistry. So, if you see a headline that says, "Aliens Found," or "Life Discovered in Space," remember to take it with a grain of salt. Now, when you start looking at this from a methodological perspective, things start to get even more fascinating. The reason we're able to make these conclusions is because of the high-quality data being gathered from multiple independent instruments. The Swift Observatory, which operates above Earth's atmosphere, has allowed scientists to capture ultraviolet light, providing us with chemical signatures that would be impossible to detect from the ground. The Spherex telescope, on the other hand, is providing complementary infrared data that's revealing even more about the chemical makeup of 3 Atlas. Together, these 2 observatories are giving us a fuller picture of what's happening with this interstellar comet, and it's giving scientists more confidence in the data. The fact that 2 separate methods are pointing to similar conclusions is a big deal. It increases our confidence that we're on the right track. But there's still some uncertainty in the data, especially when it comes to abundance ratios. The exact amounts of water, organics, and other chemicals are still somewhat unclear, and that's why scientists are being so careful with their interpretations. The important thing here is that the data is reliable, but we're still working through the uncertainties. And those uncertainties are a key part of scientific progress, Every time we gather more data, the uncertainty gets squeezed into smaller corners, which helps refine our understanding. The operational impact of these findings is something that shouldn't be overlooked. The water production rate, for instance, is critical for mission planning. We're talking about 40 kilograms of water lost per second, and that's happening far away from the sun. If this rate holds up, it could change how we approach future space missions to other interstellar objects. Right now, we're working under the assumption that comets are dormant rocks until they get closer to the sun. But if objects like 3 Atlas can remain active at such a large distance, mission planners will need to rethink their strategies. Comet coma structures, dust hazard envelopes, and photochemical evolution will all need to be reevaluated. This isn't just a theoretical exercise, it's a matter of mission risk and planning for spacecraft that may one day explore similar objects. As mission planning priorities shift, the funding and resources devoted to studying these objects will increase, making 3 Atlas and others like it more strategic targets for future research. Here's another important aspect. The data from SphereX, while promising, was released as a work in progress. This is important because it means that we need to approach these findings with a healthy dose of caution. The results are solid, but they're still not the final word on the matter. Peer review and further analysis will help sharpen our understanding. And this process of refinement is critical. Science is about testing hypotheses, making adjustments, and then retesting. So, while the current picture looks promising, it could still change as new data comes in. Let's turn our attention to 3 Atlas's behavior around its December close approach. During that time, the comet brightens significantly after its solar flyby. What's happening here is more than just surface material being exposed to sunlight. As more material gets heated, it starts to vent into space, causing changes in the object's outgassing behavior. In essence, what we're seeing isn't a static object, it's a dynamic chemical lab in motion. The surface composition is constantly shifting as different layers are exposed and heated, and this is why the current data is so critical. As the object moves farther away from the sun, we'll likely see less dramatic imagery and more data-driven analysis happening behind the scenes. This phase is crucial because it's where the real breakthroughs will occur, but it's also a time when public interest could wane. Still, for those who are following the story closely, this is when the highest value interpretations will be made. If you've made it this far, then you're exactly the type of person who values careful analysis over the latest viral science headlines. Please give this video a like so it can reach others who want to focus on the real evidence rather than sensationalized claims. And, if you haven't already, subscribe to stay up to date with the next round of findings. There's much more to uncover, and we're just getting started. The journey from speculation to measurement-heavy science is an exciting one, and it's about to get even more thrilling.